Hello, this is a presentation on a paper entitled Variational Autoencoder for Regression, Applications to Brain Aging Analysis by Zhao et al. 2019. Presentation is by me, Daniel Brennan. I'm part of CUNY CNC, and this course is hosted by CCNY Computer Science. So a traditional variational autoencoder, or VAE, aims to infer a distribution with a variational procedure leading to an encoder network, Q phi z given x, and therefore we can generate data and images by sampling from an underlying prior Gaussian distribution, which is z, and that generational network is p theta x given z. Recall that we must use a variational procedure due to the intractability of the posterior, hence the reason for q phi substitution of p theta. There's been a lot of success in using this type of network for brain images, for example, denoising and clustering, but as of yet for regression is not quite successful. So the motivation behind this paper is that traditional VAEs are nice, but we would like our latent variables to be more structured. And so what if we could structure our latent variables along a dimension we care about? Basically, can we do regression with these things? And if we are able to accomplish this, we're able to investigate the latent dimension. So in my last paper, or in my last presentation rather, I argued that in the image on the left, which is the latent space of an autoencoder trained on MNIST, the left side seems to be more curvature than the right side. I don't actually know that for sure. It was just an observation, but it would be nice if I could actually encode that into my latent representation and condition my latent variables on something like curvature or something of interest. So this leads us to the disentangled VAE. The disentangled aspect of this means that the latent space dimensions are related to a single outside factor. So the citations number 6 and 7 above are good resources for learning about this. We want to explicitly formulate the conditional distribution of latent representations on the variable of interest, meaning we want to condition z on c, and this network ends up being a combination between a traditional variational autoencoder network that models latent representations of, in this instance, brain images, and a regressor network that aims to predict, in our instance, age, but it can be any covariate of interest and any sort of data as x. So in this experiment, as noted, we're applying this to brain imaging. So age has a significant effect on brain matter. Gray and white matter degenerates over time and with age, and so therefore decreasing brain volume and increasing negative spaces such as the ventricles are observed. So not only do we want to encode brain images in a more compressed dimensionality, but can we explicitly condition this representation on age? And so what we're doing here is we're using the brain images as our x, and age is going to be our c. So instead of using a single Gaussian prior to generate z, we're going to explicitly condition z on age, c, such that the conditional distribution p of z given c captures an age-specific prior on latent representations. So the accomplishment here is that z actually can change with respect to c. So this is the accomplishment of the latent generator, which is a product of the regressor network, which is applied to the data itself. And so here, as I've said, QCX is the regressor network, essentially a feed-forward regression network with the uncertainty of the prediction and its uncertainty as outputs. And so therefore, QC given X is a probabilistic regressor. And we're going to just use a regular loss, which is slightly modified to include this probabilistic regressor and the latent generator. The results of this experiment, which were applied to a cropped image of the ventricles, which is probably an area of interest for age analysis, shows that the ventricles do expand with age, and we can capture this latent representation with our autoencoder. So the first row of images here are generated images at different ages, and we can see on the rightmost heat map image, which is a Jacobian determinant map, all this means is that if we were to fit the images together, the part of the image that has to move the most or morph the most is just the hottest areas, and so that's obviously the ventricles. A nice facet of this type of network is that, as we mentioned, our latent space is really nicely organized. So here the heat map is age, and so the color here corresponds really nicely with at least one of the dimensions. This is a compressed representation of multiple latent dimensions down to 2, but we can see compared to just the traditional variational autoencoder, the latent variables are much more organized, and that's on purpose. And at the end of the day, we actually get a slightly better R squared when we incorporate this into our regression network. So in predicting age with an autoencoded network, an auto-encoded representation of brain images, when we condition that representation on age explicitly, we actually get slightly better results when we try to predict age from those images. So now we're going to look at some code implementation of this. And this code is mostly adapted from actually the author's GitHub, who provided a toy example of this network for us to look at. And so what we're doing is we're loading just a toy data set, which is an X, consider this our data, and then Y, consider this our regressor or our covariate of interest, which is going to take as inputs both our covariates and our data itself. So we're going to boil down and we're going to get a slightly lower dimensionality, which is going to come here to enter X2. And then we are going to actually do regression on this. And with a simple dense network, do regression and get what we predict to be our covariate, and then how sure we are of the covariate, so the standard deviation, basically. And in the way that a traditional variational autoencoder works, we're going to get the Z and the Z variance, and then using the reparameterization trick, we can get the Z and the R in actually the same way. So we're going to just sample both of these, and we're going to multiply the variance, the log variance, or the standard deviation by an epsilon standard normal distribution, and that's going to do our sampling for us, so we can do backpropagation through both the R mean and the Z mean and the log variance of both of those. Lastly, this PZ mean is going to be how we condition Z on R, and we'll look at that more closely when we get to the loss. So the rest of it is just pretty standard. We're building it back up to the original dimensionality. And so our overall model will be a decoder run on the encoder. So the encoder is putting out the Z's, and the decoder is decoding those Z's back into the original dimensionality. And we can look at that here. We want to look very closely at this loss. So the reconstruction loss is just how close is our reconstructed image to the original image, or how close is our reconstructed data to the original data. And that's just with mean squared error. That's very straightforward. Here is the term that we're very interested in. So instead of just being the square of Z, we're actually going to take the difference between PZ and Z, so that Z ends up being closer to the Z distribution, which we are conditioning on our covariate. So this is the term that is most important for kind of accomplishing this goal. And lastly, we have a label loss, so we actually want our autoencoder to be able to do regression. And so we're just going to take the mean of all of these combined. And we'll do some quick training on this. And we are able to accomplish regression with varying degree of certainty. R squared is 68, 69, which is not horrible. And then the best part of this is that we're going to look at the visualization of the latent space, which is going to be highly ordered here along the Y dimension. We've actually condensed our 8 latent dimensions down to 2 rather, and we can see that it's very, very highly structured, where the color of this is actually our covariate Y. And so as the color sort of gets warmer to yellow, we see that it's very, very structured. Okay, so now we're actually going to break this. This might take a little bit longer than I expected. But basically, we're going to retrain this model, except we're going to take out a few points. So we don't need PZ anymore. We're just going to have Z and R be our outputs. And then in our encoder, we actually don't want to output PZ mean anymore. This should be good. Yeah, we've gotten rid of PZ. So it's basically essentially the same network, except we just don't have PZ coming out. And now we're going to go take our loss, and we're going to actually modify our loss slightly. So this loss, we still want the label loss, and we still want the k-out loss, but we just want this square to be the Z mean. So now we don't care whether it's being conditioned on our covariate or not. We're simply just going to do this. It's an error, but that's okay. So we should still be able to accomplish regression. And so lastly, we're going to train our network on this here. And so we don't want PZ mean as an output, but otherwise we'll be basically identical. Okay, so now we're going to go back to our visualization. And so with our validation, we see that we can actually do basically just as well with regression. But the most interesting part of this is now that we haven't conditioned on the covariate of interest, our latent space is going to look a lot different. Oh, whoops. We don't want PZ mean here. our latent space now is going to be completely disordered, and it looks like a really nice bivariate Gaussian. But you can see, especially in terms of the colors, that this is completely unregulated with regards to age. And so by just getting rid of that very simple term, we've completely eradicated the deconstructing or the disentanglement of the latent space. Okay, so that's how this works in practice, and this is deconstructing basically the most important part for keeping your latent variables in line. Thanks.